Attention! Can the judges please start wrapping up their judging within the next few minutes and return the score sheets to Chelsea and Allison at the blue judges table? Thank you. Victoria's doing it. I'll get that done. You guys can come sit. I made a mistake. My bad. Feel free. It's up to you. Go for it. It's up to you.
All right. Hello, everybody. I'm Victoria Almeida. I'm a junior in mechanical engineering.
I'm Nicholas Kortenhouse. I'm a freshman and also doing a mechanical engineering degree.
And welcome to our 13th annual Innovation Showcase, FED Innovation Showcase. It's not changing.
Cool.
All right, so once again, sorry for that. We are going to begin now in this Innovation Showcase, our presentation and our PowerPoint aspect of this whole showcase. And to start it off, I would like to welcome, if it goes, I would like to first welcome Dr. Joe Gavrao, our chairman of the Department of Mechanical and Industrial Engineering. Do you want to hold that?
I'll put it there. Great, thank you. Welcome everyone to the Innovation 101, the Mechanical and Industrial Engineering Fundamentals of Engineering Design Showcase. So I just want to give a little history of this event. This is the 13th event, and it was started by Professor Mani back in 2011. The first edition of it had 90 students in 30 groups. Since then, it has been running continuously for 13 years now. You can see all the brochures in the front out there. And it's significantly grown in both in terms of number of students and in the complexity and the kind of projects that they're undertaking. Over the years, more than 1,700 students have participated in the showcase, and for most, it was one of the highlights of the time they spent here at NJIT. The MIE Innovation Showcase has been an inspiration for other such activities on campus, such as the NCE First Year Design Showcase. This year, we have 167 students participating and 57 teams mentored by Professor Mani and Professor Moon. Professor Mani's section worked on reverse engineering specific devices, which you can see on the right side here. They picked a device and dismantled them, made detailed measurements of each part, then drew the parts using the CAD software Creo, and figured out how all the different parts fit together to get a better understanding of how the devices function. Furthermore, they modified the design and printed them out in the makerspace. Professor Moon's section, using the theoretical knowledge and CAD skills that they learned in class, worked on specific designs and drew CAD drawings using SolidWorks and built prototypes making extensive use of the makerspace, tested the prototypes further, iterated the design to produce functioning manufactured prototypes. Those you can see on the left side there. Some of these projects are open source and they'll be added to online repositories which anyone in the world can download and develop further. As you can see, this year's projects range from pencil sharpeners, clip-on fans, Da Vinci clocks, Hexberg spider, prosthetic devices, mobility devices, and exoskeletons. And also today we have senior engineers from local industries, faculty and alumni serving as judges. We have family members of participating students here to see what their budding engineers are accomplishing in their first semester here at NJIT. We have alumni of the Innovation 101 Showcase who have dropped by to reconnect with the program that made a lasting impact on them. And I want to thank everyone who is here for attending and making this a successful event. And I want to especially thank both of our keynote speakers. Roena Fernandez Chaudhary is a Senior Scientific Director for Chemistry, Manufacturing, Controls Leadership in Global Product Development and Supply at Bristol Myers Squibb. Roena graduated from our department in 1989 with a BS in 1989 and in 1991 with a master's, both in mechanical engineering. Our second keynote speaker is Mr. Greg Livelli. He's the Senior Vice President of Innovation at Harvey Performance Company. Greg is also an alumnus of our department and graduated in 1992 with a bachelor's in mechanical engineering. I welcome both Roena and Greg, and thank you for taking the time for being here with us. Now, I just want you to imagine that a few short months ago, the students who participated in this showcase first stepped on campus here at NJIT. It is really important to remember that this is the third month they've been here at NJIT, and within 3 months, they have accomplished so much. It really is an impressive achievement. It really sets them up to succeed here at NJIT, helps them develop character and discipline, and a can-do attitude, and learn the value of hard work. All this accomplished in a setting of teamwork and done with passion, as Professor Money likes to iterate. The organizer of the Innovation Showcase took the dedication of many. I'm sure Professor Money is going to thank a lot of them, but I want to acknowledge two. A special thank you is to Dr. Swapnil Moon, who teaches some of the sections of FED 101. He has brought in a number of innovations, expanded the scope of the course, and included in it making extensive use of the makerspace. And secondly, the person most responsible for the success of the showcase is Professor Mani. For 13 years now, through his dedication and passion, this has been a very successful program. He started this as a pilot program in 2010 when few people thought it would work. Since then, he has been guiding it admirably, and it has been growing and improving every year. In the 13 years, he's inspired thousands of students. Professor Mani really puts his heart and soul into it, and it clearly shows, as you can see the results. And I'm sure you all will be happy to know that Professor Mani received an Excellence in Teaching Award last year, primarily for what he's done with this showcase. A big thank you to Professor Mani. And finally, the most important of all, the students who participated in the showcase. I want to congratulate each and every one of you. And I want you to remember that this is just the beginning. And we really expect much more from you in the years ahead. And we look forward to your future accomplishments. So congratulations on a job well done.
Thank you very much, Dr. Rao. And moving on, it's crazy to think that this started 13 years ago in 2010. I mean, I was just in 2nd grade.
I was in kindergarten.
And that's a pretty long time if you ask me. So it's really important because through everyone's presentations, a big part that's been promoted with this whole topic is the inspiration within everything. And you can see how the students moved from, at the beginning of the class, being able to just do a plate with a hole to now doing this crazy project, which Nicholas is going to talk about.
So going from plate with hole, we learned the simple just extrusion tool in order for us to design many different shapes. However, from there we elevated to do things like revolve, sweeping with a path, blending, in order to create different shapes, as well as features that can ultimately combine and form models such as the Da Vinci clock. We also learned how to do gearing with a master model and changing the parameters. That way it all adds up and meshes nicely together. This also allowed us to learn teamwork and being able to divide up the work and be able to rely on others in order to come together to make a thing. After all, not one engineer can design a whole product. Another great thing with this project was, yeah, again, the hands-on experience. Whoops. So how many of you guys have worked in the makerspace? Many of you guys. So first, now let's also introduce the maker of the makerspace, Dean Mushi Kam. That was rough.
Thank you so much. I feel like a very lonely electrical engineer among all these mechanical engineers around here. In any case, I'm very pleased to be with you. I'd like to express again thanks to the individuals who made this possible, Professor Rao, Professor Mani, Professor Swapnil Moon. And I also would like to thank the judges who gave us of their time and attention and talent. And indeed, it is remarkable to see you students how far you have advanced. In fact, I recognize some of you from open house when you just came to look at NJIT and ask me questions like, how good is this department, and questions of this nature. And I'm glad that you have selected to come here. And I think that by looking at what you have achieved, it demonstrates that you have made the right decision. Professor Rao indicated that some student told him that this was the highest point of their experience at NJIT. I hope this is not true. In other words, I hope that it is not that you came here and then from now on it's downhill. It's not. There are many other challenges and many other great design teams and design opportunities that you will have. Among the things that we are trying to accomplish in this exercise, in this class, is to accustom you to teamwork. Engineers very seldom work all by themselves, and teamwork, as I'm sure you have already witnessed, is very useful in the sense that it gives you different viewpoints and input from different individuals from different backgrounds. And sometimes it's pretty annoying when someone is insisting or someone is disappearing for a couple of weeks, and all these experiences, I think, make you better in future projects. I also am sure that you have found out, especially those of you who did reverse engineering, how much wisdom is there in the tools that you have reversed engineered. Sometimes things that we take for granted, and you realize that actually everything is there for a reason, and if you try just to arbitrarily make it better without analyzing it, you actually make it worse. It is very interesting to see the tools that you are using. I'm thinking about how would a class like that look if we had it 20 years ago, right? There will be many rulers and ink, and today it is all computerized, and you have excellent tools for calculations, for estimation, for measurement, for visualization, and for imaging. It was also, it really feels, by the way, that 20 years ago, and I was around, almost feel like it was the Stone Age compared to where we are today. The makerspace was mentioned a couple of times. And I know that students at NJIT have a classroom and a gym and a makerspace, you know, like another tool in our hands. But you should know that there are very few students in other engineering schools that have access to the kind of makerspace that we have here, in terms of the wealth of equipment and in terms of the fact that all of you have access and can continue to work there. And I encourage you to make the makerspace your second home when you are here. I was very impressed with all the tools that you have used and all the work that you have done. I don't know how many of you have already used AI in your design. Anybody? But it's coming. I'm sure that in 2-3 years when we come here, we'll find that half of you are also using AI in order to do that. And all of us will need to learn the new AI tools. And rather than be afraid of them, as you read and hear too often on news magazine and such, we need to endorse them and make the best use of them. So you have done very well, and we will have you for at least another 3.5 years. So I'm looking forward to meeting you, working with you, and seeing the further heights that you will get to. Thank you.
Thank you, Dr. Cam, and I'd have to agree with the teamwork and with the makerspace. Very thankful for the makerspace because working in a research and during the FED project, it really does help, and it's really crazy whenever I go into the makerspace, seeing from everyone from research, from projects, from just doing classes. They have so many projects they're working on, and they're all really cool. And personally, when I did my tour, it was my selling point for NJIT. But to talk more on NJIT and previous speakers,
We would like to introduce Rowena Fernandez-Chardry. She's a leader with the Global Project Development and Supply at the Maersk Squibble. Rowena also handles cross-functional strategy teams of scientists and engineers developing active ingredients and drug products.
Thank you, Victoria. Thank you, Nicholas, for the introduction. And thank you to the faculty, the administrators, Michael Smullen, who was my first contact to inform me about this event, to Professor Mani, who convinced me, yes, you're going to speak today. And of course, to all the freshman engineers who are here today, thank you for the invitation to spend the day with you today. So it really is a great experience to be back here on campus after so many years. You may have heard I graduated back in 91, so it's a while, definitely much older than you guys. And just walking from the parking lot to the student center made me reminisce, you know, the times that I walked around the mechanical engineering hallways, working in the labs, hanging out downstairs. I think back then there were the table tennis, ping pong tables, still there. There was a bowling alley, still there. Oh, I'm sure it's much better now, yeah. No? What else? Oh yes, and I'm kind of embarrassed to admit I was also thinking I saw the brand new library from a distance. I was not able to enter yet, but I thought, how many times did I fall asleep while studying? But at least it evoked those memories back. And I really am proud and honored to be here, to be as one of the judges, and be impressed by what I've seen, what you've demonstrated here today. I just can't fathom, actually, while I was listening to the presentations, the designs, and compared to how I was when I was a freshman. I'd like to use the same term. I felt like I'm from the Stone Ages. I was a freshman, and we had Engineering Graphics 101, pencil, paper, ink, T-squares. You run inks, they cross all over, you have to repeat. My second semester, we started AutoCAD. In fact, in graduate school, I was one of the TAs for AutoCAD, and I thought, I'm pretty, cool. I know AutoCAD, and I'm teaching freshmen. But here you are today, freshman semester, working on SolidWorks. I was a senior when SolidWorks was introduced to us, and graduating with a bachelor's degree, knowing how to do SolidWorks. Again, I was, in the field that I was working in back then, it was pretty like, oh, these folks who knew SolidWorks were cool. They knew the latest technology. And here you are, freshman year, first semester. So I'm truthfully really blown away by the challenges that NJIT has given to you and is still furthering to challenge what you can do in the future. So, oh, I'm sorry, I'm not used to holding this actually. So let me see here. Oh, there. Sorry. Well, I do want to say that before I start talking about my career journey, because I was told one of the ways, one of the topics I should talk about should be about maybe examples of my career journey as a mechanical engineering graduate and what have I done in my career. But first and foremost, I'd like to congratulate the freshmen. The freshman engineering students, the fact that you are here and what you have done is an accomplishment. So I congratulate you. Like I said, I am honestly in awe in what you've done. So looking back at my younger self, I was always excited about learning math and science, and I'm sure most of you are. That's why we're in this field, right? So that's a commonality amongst us. But what's also, when I was searching for a college course, what really excited me was the definition of engineering, which is a combination of math and science, and that it is to solve real-world problems for practical uses. So even today, at my age today, just reading this statement excites me. It still excites me. I do STEM outreach on behalf of the company that I work for, as well as voluntary work. And when I speak to the younger students, middle school, high school, young college students, it really does excite me to encourage the younger generation to be in a STEM field, not just engineering. So for myself, looking back then, you will realize, I keep saying back then because that's my point of reference. There were probably 40 plus types of engineering programs. And today I think I understand there might be 50, 60 plus types of engineering programs. And so back then I was looking at mechanical, chemical, biomedical, industrial, environmental engineering. That's still a long list to narrow down. But from that, I selected my top 2, narrowed it down to mechanical and chemical engineering, and obviously I ended up going with mechanical engineering. And the reason why I selected at least the top 2, mechanical and chemical, and sorry for those electrical engineers, I know you go according to your passion. Back then, my thinking, and it still is, that both mechanical and chemical engineering, at least in the field where I'm in, tends to give a broad scope of engineering and gives you a very versatile background that can lead you to many career paths. And so, because I was still curious with the other fields of engineering, I made sure that I also took electives covering biomedical, industrial, and environmental subjects. And maybe one last thing, instead of saying that I keep reminiscing what I've done here at NJIT in my undergraduate years and graduate years, I do remember going through material science class, working on the CNC machines. I'm not sure if that's still being used. Oh, great. And then I remember the lab with polyethylene pellets, and we made spoons out of that, and we looked at different parameters. I'm not sure if you still know. That was fun. And of course, one thing to mention, back then, the new technology was stereolithography, very early form of 3D printing. So that was another cool introduction that I learned from NJIT, going out into the real world and having these tools. I knew stereolithography, I knew CNC, I knew SolidWorks. I mean, you get equipped here at NJIT with the tools so that you have a cutting edge when you get out of college. So let me just quickly talk about my career path, and I will shorten it to just 3 buckets in my career path. And I will start off with, to be honest, with my co-op engineering position, because it might sound trivial, but it does impact how you can leverage your work experience even before going into a true full-blown professional career. So I started out as a co-op engineer, as a project management assistant, and I was a senior in college. And I'd like to plug in at this point that it was an advantage to be at NJIT, which is one of the first and few universities at that time who offered a co-op program. So I'd like to encourage you to look into that program. So in this role as project management assistant, I assisted project engineers managing timelines for lab facility transfer. I gained knowledge in lab construction, lab equipment, building equipment, as well as preparing Gantt charts, PERT charts, and identifying critical paths. Actually, I think 1 or 2 of the presentations I saw showed some Gantt chart and PERT chart, so I was very pleased that even as a freshman, you're learning this early on. My next role, as you can see here as reference as career number 2, was also a co-op position. So again, I took advantage of what the NJIT co-op program offered. Back then, I was a process engineer with Johnson & Johnson Personal Products Division, and this I took on when I was in graduate school. There, I worked with senior engineers to design and conduct process experiments on feminine hygiene products. And back then, I was the only female out of the 50 engineers. But that wasn't really daunting. They were all wonderful to work with, and I had a lot of learning experience. And during that position, I do recall opening up my books to apply what I learned in fluid dynamics, thermodynamics, and machine design. So what you learn today is really useful. So as you can see, just from the first 2 very early experiences, even though I was still green in my career, having an engineering background allowed me to be versatile and allowed me to explore paths in different industries, lab construction and personal product industries. My third career, which is where I recognize my passion, which is to apply science in developing medicines and drug devices that help patients. It is with the pharmaceutical and biopharmaceutical industry where I've spent most of my professional years. I began as an R&D, research and development process engineer, and climbed the ranks through years of experience. Working in R&D, I designed and performed pilot plant experiments. My work incorporated engineering calculations, statistical design of experiments. In fact, here's another thing that I learned here at NJIT as a math elective in graduate school. I learned DOE, fractional factorial designs, which I proudly applied at work and happily explained it to my colleagues. My job entailed selecting manufacturing equipment from pilot scale to commercial scale, which also required us to perform process scale studies. Now, upon solidifying a process, we would then transfer the manufacturing technology to various manufacturing sites. I had multiple projects in Puerto Rico, Ireland, Italy, Belgium, and Switzerland. So I really had a wonderful opportunity to travel. I also had the opportunity to travel a couple of times actually to Japan, and of course different parts of the United States. And I would say in gist, the goals for most of my work, even today, even though I no longer work in the lab, I work with multiple backgrounds of scientists and engineers as a cross-functional team leader. The goal typically is to enhance process efficiency, improve cost effectiveness, and resolve production issues. So I was involved in manufacturing and developing tablets, capsules, nasal sprays, injectables, pen injector device, and radio-labeled materials. I just want to gloss through a few examples where you can apply your engineering background and connect on how do you connect engineering to developing products. I worked on Nasonex nasal spray. I would like to think that some of you use this for your allergic rhinitis. I worked on developing biologics for injectables, capsules and tablets for cancer and other indications along those lines. I am not a true packaging engineer, but with my mechanical engineering background, I worked on an injectable product, the one on the far right, on the packaging device. So that's another way of applying science and pivoting your knowledge to something else and be versatile about it. I was also excited to work on cartridge pen injectors and aerosol products. From here, I'd like to give some examples on how engineering calculations are applied in the pharmaceutical and biopharmaceutical industry. So on this slide, you will see how computational fluid dynamics can be applied to optimize tablet drug spray coating. I met earlier today 2 PhD candidates, Shivam and Ketan. I'm not sure if they're here. There you are. And you told me that you're focusing on CFD, so I was, yeah. So this is super simplified version. This is baby stuff for you. But this is an example how you can apply CFD for tablet spray coating. So for this project, I worked with a software engineer and a mechanical engineering consulting firm to repurpose a CFD software application. So the computational model was developed to analyze varying factors, the droplet size distribution, the concentration, whether it's aqueous or organic solvent that we're using, the inlet air temperature, the air volume, and the spray angle. So multiple factors. And upon determining the process parameters, using the CFD model, we would then execute experiments, a campaign of experiments using fractional factorial design of experiments to confirm the design space. So by using this CFD modeling approach combined with design of experiments, we were able to minimize the number of experiments. So if here, from this example, I show 6 factors, that's 2 to the 6, so 64, we could have done 64 experiments, but that would have taken so much time, so much effort, materials, et cetera. But then when you combine the modeling with the math behind it, the factorial design math, then we were able to reduce the number of experiments to 8 or 10, thereby minimizing the number, the use of materials, operational resources, and minimizing time. So overall, we saved hundreds of thousands of dollars. And this is just one project because you can always apply it to different types of projects. Another example that I worked on is droplet size analysis for simulating aerosol deposition in lungs. And for this project, actually I volunteered to learn back then to use a laser diffraction equipment to analyze droplet size from different propellants. So that was there was a time when there was a limit in using Freon for aerosol propellants, and we were transitioning to the new propellant system. And so my job was to look at droplet size and simulate how would these droplet size, based on the formulation, and how does that how will that impact as a patient would inhale and simulate how it enters the lungs. So that's another application of science with the background in engineering. Now, part of drug development is learning to use the equipment. On this slide, as an example, is a tableting machine. And as a process engineer, you will have to troubleshoot. You need to learn to troubleshoot the process so that you can yield quality product. In this case, yield quality tablets. And by modifying perhaps the powder feeder, the vibration, the pressure, etc., you can then have a better powder flow and better product quality. So you will then have to rely on gaining experience, learning how to use the equipment, because you will then later on also rely on that experience, so then you can purchase new equipment or compare equipment as you do the technology transfer. So this is one of the examples, just to simplify what I've learned in my growing years. Here's another example. You know, actually, this is a simple vial filler for syrups. And I can always continue to give examples, but I don't want to prolong all these examples. But essentially, the message that I would like to convey to you is that with an engineering background, you will be exposed to learning so much and learning to expand your abilities to learn even more, because learning will never stop, right? It's part of the thrill of being an engineer. And so just imagine that could be a lot of fun. I would like to actually end with this slide with just a few words to ponder. I was thinking the majority of the audience here are freshman engineering students, and recalling what I was back then, I had a huge thundercloud in my mind. What am I going to do? What if I don't like mechanical engineering? What if my passion is still in chemical engineering? So on and so forth. Just a lot of thundercloud. But you know what? It's all right, because a career path won't always be clear. There are times even in my professional career, I have my own thunderclouds, and I wonder, what do I do when I grow up? Sometimes I'm thinking, what do I do in the next 5 years when I grow up? But do remember to count on your advisors, your mentors. Don't be afraid to ask questions, whether you're in college or even when you move forward with your future work. While you're here in school, make sure you ask questions to your advisors, your professors. And when you move on, keep on asking. Seek help from mentors. Get as much real-world experience as possible. Take advantage of NJIT's co-op program. And I think I saw in the faculty dining hall a couple of, I guess, professors, colleagues here from the career development. So reach out. I think they'll be helpful. And sign up for undergraduate research. When you embark on your career, don't be afraid to raise your hand, to volunteer for projects that are not so appealing, because you'll learn. And one day, who knows, that might be the hit, and that might be what could pivot you to another exciting journey, to another project. Also, all these suggestions about real-world experience, volunteering, actually these are little tidbits that may give you a cutting edge over your competitor. So we also know engineering is a very rigorous course. It's not a joke, and I don't want to sugarcoat that, oh yeah, it's a lot of fun. It's a lot of hard work. And when things get rough, just remember to keep that inner drive. Find a good set of people who can keep you consoled, to keep you going. It's important to keep your conviction. Having an engineering background and having an engineering education provides a robust foundation which can give you versatility to pivot to many career paths. You don't have to stay with a true, highly technical career, because you can always use your technical background and venture more. In fact, I would like to encourage you to gain a higher degree, master's or PhD. That's something highly encouraged. And being engineers, we are oftentimes stereotyped being too technical, too geeky, too nerdy. That's fine. Yet don't forget that you also need to develop your communication skills. Without enhancing your communication skills, how else will you convey your brilliant ideas? I know we have a lot of youngsters here, and even myself, I have to keep reminding myself on ways to improve communication skills, not just in presentation, but written, because that's how I can convey the thoughts, not just from what I have, but also from the team that I lead. As you advance, I'd like to, I don't want to sound like I'm pontificating here, but I do think it's important to say the simple words, thank you, right? Thank the people who helped you along the way. Your parents for their guidance, the times that they helped you with your homework, or even for paying your tuition. And of course, thank your teachers, your administrators. You may not feel the impact right now, but myself, as I look back and knowing the vision that the professors and administrators here, their vision to bring this to you as students, the vision of what they plan to offer you as courses, for your courses as you go through your engineering education, you definitely need time to reflect and thank your professors. Thank anyone who has touched you along the way and helped you advance. And as you've heard the other speakers, they emphasized teamwork. We've been trying to learn teamwork since our kindergarten days, right? We've been learning to share our drink, our sandwich, or our toy. You will continue to learn, and which is essential, because I don't want to. I think there's. I'm not sure if the slide is showing. Oh, yeah, that one, yes. Yes, I took this because I really think that teamwork, as the saying says here, when I is replaced by we, even illness becomes wellness. Thank you for your attention.
And I would like to thank you, Rowena, because I'd like to thank you also for sharing your opportunity, sharing what you've gone through, your different careers, and sharing it with the first years as well. And I think it's really important how you mentioned the passion within each different stage in your career. And I think it's really important for everyone too, with the career, the struggles that you might be facing as first years, maybe that uncertainty in like the future years and all of that. I think it's important to stay where your passion is at. And as Professor Mani really likes to say, if you're in his class, the passion is all that really matters with everything. It's really what's going to guide you. And up next, I'd like to also introduce and welcome Mr. Greg Livelli, who went from marketing and engineering to chief product officer for Nidex Appliances. Livelli, through leadership and influence, led vision and transformation and infused a new culture in developing and execution of corporate products, technology, and operation strategies. Please welcome Mr. Greg Livelli.
Good afternoon, all. Can you hear me okay? And I want to say thank you to the faculty, the first year engineering students, and the opportunity to be here. I am truly humbled and honored to be an alum of NJIT. First, again, congratulations. You guys have embarked on a journey that is going to be both challenging and rewarding. The next few years are going to be exciting ones, probably filled with caffeine-laced evenings, debating boundary conditions. I'm a flow guy from that side. Or do weeder classes really exist? You know, how hard and difficult this is going to be. You'll start questioning some life choices. But for engineering, for us as engineers, it's a calling. It starts with a deep-rooted passion for innovation, problem solving, and design. It's a discipline that requires a lot of commitment, significantly a lot of commitment that's here. So, you know, it can be overwhelming at times, especially when you're watching your friends on Instagram or Snapchat and they're out partying while you're studying. I didn't have that. My sophomore, who's in Butler, tells me that she sees that, and why does she have to work so hard? All right. I'm going to talk a little bit about integrity before I go on. But plagiarism is not something that's acceptable, and we're going to say similar concepts here. So we didn't plagiarize concepts, but hopefully you'll see something that goes forward. So as your semester, first semester comes to the end, you might be contemplating, are you willing to make this commitment for the next 4 years? All right? I was, and I'll tell you a little story about that in a bit. That's not to suggest that if you are struggling, you should quit or find another field. If engineering is for you, then grind it out. I promise you it'll be worth it in the long run. All right. So I got asked to talk about passion from here. So my engineering calling started as a childhood fascination of taking things apart, putting them back together. I was captivated by the way things worked, from dismantling my own toys to building Legos to turning my ideas into reality. I started out as a tinker. Any other mechanical engineers, thinkers? Yeah, usually that's how we get there. So my first memory goes back to taking apart the family's answering machine. Anybody know what an answering machine is? Okay, you probably saw it at your grandparents' house or something like that, right? So, it was broken. I wanted to see if I could fix it going forward. If you don't know what an answering machine is, it was this electronic device that hooked into your phone system that had a cassette tape in it. Again, another thing that's obsolete in the world today. And it took messages for you when you're away. Today, it's called voicemail on your phone, all right? So it's there. So I eventually found out what was wrong. I fixed it. There were some parts left over, but it seemed to be working fine, so I just kind of moved on, okay? This eventually led me to my first official step to establishing a career by attaining a mechanical engineering degree from the best institution in the world at NJIT, and it's always had a special place in my heart. And it's not just the world-class education that you're going to get here. It's the theoretical and practical foundation that will be instilled in you, that not just how you go through college, but in your professional life and your personal life as well. Right? So growing up, I was taught about hard work. I was told to get a job at 14 years old. I worked entirely through college, and I had a work ethic in me that I believe successfully positioned me in life. But balancing school, work, and the extracurricular activities was not easy. So working hard is part of your first year studies. Again, I think some of you are probably overwhelmed. Keep going, okay? After my first year, I questioned, should I continue to be an engineer, all right? And it was crazy hard. And I was at the top of my class in high school, but man, it was really difficult when I got here. So I always remembered something my father said to me after my first year. He said, understanding what you love, what your strengths are, and what you're interested in is the first step in igniting your passion. Okay, that's 3 steps, but I wasn't going to argue with my dad about that from that side, all right? But it's not simple as what do you want to do when you graduate. It's about figuring out what ignites your passion, all right? What gets you excited, what drives you to get out of bed every morning and either want to go to class, go to work, do something else, all right? He said, once I know that, everything else will fall into place. I felt like Yoda was talking to me with proper grammar, at that side, but, the wise things he was giving me. So now how did I turn this into a career? So going back to the words my father said, he used the term love. And love isn't a term I typically associate with engineering. To me, engineering is about perfection, structure, facts, and appreciation for intelligence that's there. However, through my 30 years plus year career, I've been asked more times than I can count, why do I love engineering? And for many years, it took me a long time to struggle to come up with a pretty simple answer. But today, I think I have a pretty simple answer. Engineers, especially mechanical engineers, do things that only other people can imagine. Okay? So it's, in fact, if it can be envisioned, an engineer can make it possible. So that's where I go back in my career now, where I work as a researcher, an entrepreneur, an educator. And what I learned at NJIT, combining that with an MBA, steered me towards a path of not just the engineering, but the business side of it as well. But NJIT gave me a solid foundation and skills I would need to work effectively across multiple disciplines, multiple engineering areas, and as I try and make the world a better place. So you could join a company like Tesla, design electric vehicles. You can work with a startup that's developing biomedical devices to improve healthcare. Whatever it is that it's important that you have passion for what you're doing, right? So to better familiarize you guys with the passion of my career, I took a lot of advice from my internship, my co-ops, mentors that are there. Project-based roles, jumping into things that I wasn't really comfortable with doing from that side. Don't be afraid to engage in those professional networks. Reach out to your professors, reach out to people, reach out to other people in the industry like me if you need help and guidance going forward. We love to provide that there. Go to industry conferences. They're usually free for students, and you can learn a lot and you can really network from that side. But I think the one thing I took most is I had a mentor that kind of guided me and navigated me throughout my career and my roles going forward. So I can tell you, though, that quest for that role is not easy, all right? I was a very passionate skier here, and actually, if you can believe it, NJIT, when I was here, did have a ski team at that point, right? Not much skiing in New Jersey here, but we did it on a regular basis. And I wanted to go out and design skis. And I moved out to Colorado to design skis, which was there, and man, did I realize that's an industry that's almost impossible to break into. Right? Not many ski manufacturers that are out there. It's more of an art than a science at times going forward. And after starting to realize what was going on, that wasn't the path for me, I'm like, what am I going to do now? That was my dream, and now my dream has been crushed. Okay? So don't be discouraged, because there is always a role for you if you're passionate about it. So I look back at the opportunities. Back in the days is the term I use, which is there, right? And I'm sure you guys have heard that a lot growing up. You used to have to find a job in the newspaper classifieds, right? Anybody know what a newspaper is? Yeah, classifieds don't exist anymore, right? You paid by letter for the ads that were there. You didn't have a full page on Indeed or something that told you, here's everything you're gonna do. And the job description was good oral and written communication skills, must have an engineering degree, passport required, right? I checked 2 of the 3 of those boxes as an American. Right? Didn't have the passport, which was no problem, that was there, all right? But traveling was something that interests me, so why not throw my name into that job? So I get my resume, I type up my cover letter, which was there, I put it in an envelope, I take it to the post office, again, not how things work today, and I'm not trying to say, we should reflect on the old side there, but mailed it. 3 weeks later, I got called for an interview. You just did one interview across the entire company that day, and I found a company that was a pioneer in flow measurement. And that was something that I was passionate about when I was here as well. And they were looking for a business development specialist. Today, that's termed an application engineer, all right, to go and build the business in Asia Pacific. Man, I was a tri-state boy. The furthest we ever went from here was Washington, D.C., after growing up in New Jersey. Now I'm going to get on a plane and travel all over the world. I got my passport. 3 weeks later, I was in Seoul, South Korea on my first customer visit. Eventually, that expanded onto Europe, the Middle East, and Africa, and I got to travel around. And it was not only doing the love of the job I had, but I was actually loving and passionate about traveling as well. Right? The other thing that it gave me was a cause, right? And I think it's a new thing, because again, I have a 24-year-old and 20-year-old that tell me, they want to work for something that's a cause, right? And not only were they developing product, but our value message and what we told customers and what we actually gave them was the ability to lower energy costs and operational cost. Again, felt like I was making the world a better place. So again, flow measurement packaged with travel, that was like bonus to me. Now I'm making the world a better place, right? turned in for me to a 20-year career in flow measurement, and eventually I was running a $2 billion flow business for ABB. Okay? The greatest part about it, besides the loving the work that I was doing there, is I've been to 104 different countries in the world. I've traveled around the world, if you calculate it, 175 times on how long I've been on an airplane. Okay? But that was the passion that drove me. I didn't have a problem getting up and going and traveling every week going forward. Now I embarked on one of the scariest times of my life because I loved what I was doing with one company, and now let's move to another company, right? And when I was kind of going through jobs, you kept jobs for longer periods of time. Today's world is 3-5 years. Try to get out of that. Getting with somebody for a longer time is better. But I was really scared. I went from a company called Emerson to ABB. I was still in flow measurement, but instead of leading a differential pressure product, which is based on Bernoulli's theorem, I'm going to lead a electromagnetic flow meter product, which is based on Faraday's law. Oh, I got to go back to my books and understand what Faraday's law is and how do I do that, and my roots to improve my knowledge that's there. Right? Faraday's law was 1832. How am I going to apply that to the real world going forward? Then I took over the entire flow measurement business, and I had to understand the Coriolis effect, the Doppler effect, the von Karman effect that's there, and et cetera, thermal mass, right? So when I was going through school, I was asking myself questions. When am I ever going to use this again? Well, here's proof that you're going to have to go back and use those things. And when I was with my passion for flow measurement, I realized I could do more. I could expand outside of the mechanical engineering disciplines into some of the electrical and chemical engineer side as well. So I became a bit more multidisciplined. Then I got enamored with a job to do something else, to move me to St. Louis and work for a company called Hussmann that did cases and refrigeration for grocery and convenience stores. Oh, now I got to learn about refrigerants, mechanical designs of refrigeration systems, cases, electrical lighting, and all that stuff. I ran the engineering, marketing, and new product development teams there. Again, continuing to learn and continue to move along. From Hussmann, then I wasn't really passionate about that job. Kind of did it for 2.5 years. My wife said to me on the beach in Manasquan, New Jersey, she said, it's sucking the life out of you. Okay, so yeah, if you're not passionate about what you're doing, it's really hard to get up and go to work every day from that side. So I decided to move on, went to work for NJIT. NJIT does motors for appliance, commercial and industrial applications, your dishwasher, refrigerators, your pumps, your compressors, and that side. Again, now I'm learning more electrical engineering skills, how rotors and stators go together, efficiency ratings, how winding copper can do that, a whole bunch of different things. But again, continuing to learn and develop new skills and competencies. Today, again, full circle back, because my internship was actually running a CNC machine when I was here. And now I'm working for Harvey Performance Company selling machining tools to those companies. I don't know how it works that way, but it kind of brought me back to there. And I'm really the leader of the innovation team. Again, that really means engineering and new product development going forward. So why did I kind of go through my work history here? Because converting a passion into a career is a journey. It's a journey of self-discovery, education, persistent searching for the right opportunities. But it's really about pushing your boundaries of what is possible. An enthusiasm for technology and a commitment to sustainability or dedication to improving the world will not only shape your career path, but it'll shape the future of engineering as well. So it's very important you continue to have that passion. So teamwork. Man, I'm impressed with the teamwork I had here and everybody that I went around to and asked. It really seemed like, yeah, it's difficult sometimes to be put in teams. I remember when I was here, sometimes I would be like, oh, if I could just do it myself, it would be easier. I wouldn't have to worry about this person's working this day, this person has class this time. How are we going to get together? But what you start to realize is teamwork makes the dream work, if you ever said that. And you need each other. Not only as you work on projects, you need each other for support as you go forward. So you're going to develop strong bonds with your classmates as you continue through this journey, right? You've already been asked to work on joint projects, so you're, beyond the, courting stage. Now you know who you are from that piece. And I can tell you some of my good friends today are people that went through the program with me going forward. And you need that community. Because the best parts I remember about NJIT was that community and the support from the professors, the support from the administration, the support from other students that were there. And I heard somebody say it today, I think it was all the way over in the back corner over there, that man, you can just go up to anybody in this school and you still get that help today. And that's the culture that's built in here for an NJIT, and I hope you guys get to see that. But teamwork is like the cornerstone of human progress. It enables individuals to come together and achieve goals that seem insurmountable when you're only tackling them alone. I can tell you the significance of an effective team in a professional world cannot be overstated, right? Your educational journey is where you start to learn how to go that and develop those skills and a driving force that's going to lead to countless success. So when you do that, you have to look at every individual is different. And that's what I kind of learned, why I said I went to 104 different countries, right? The US is different too, but wow, when you get outside, it's even more different. And everybody brings a unique skill set, experience, and perspective to the table. And you have to be welcoming to listen to all those experiences that are there. Because teamwork takes all this diverse strengths and brings them together. It's like assembling a puzzle where each piece has its place and contributes to the bigger picture. Okay? So when you have team members who excel in various areas, you're more likely to cover all the bases and accomplish those tasks. If you think of problem solving as a skill, a well-coordinated team can brainstorm, analyze, and devise solutions more effectively. And different viewpoints, maybe you don't always agree, right? But different viewpoints are going to give you a wide range of solutions that you can agree on to how to go forward, and that's the likeliness of finding the right answer. Right? Being part of a team is also highly motivating. Right? They also typically, teammates spur each other on to perform at their best, creating an environment of healthy competition. Right? I use the term peer pressure. I know we've been told peer pressure is a bad thing. Right? Peer pressure is a very good motivator used in the right way as well. All right? Knowing that others are going to rely on you for success instills that sense of responsibility and accountability. And that's where it really matters in the workspace. And you're going to develop those skills as you go through here. Let's flip to the other side of the coin. When you face obstacles, right, or setbacks, a team is there to support you through that process by encouraging and motivating each other to keep moving forward. Don't give up. Have a collective resilience to have meaningful change in overcoming those challenges. And it's not just about individuals working side by side. It's about individuals working together harmoniously to achieve a common objective. It's about recognizing the power of collaboration and understanding that together you can accomplish what seems impossible on your own. I want to just kind of finish up with your journey from NJIT lecture halls to the structured environment of the engineering industry is going to be an exhilarating transition. Okay? When you graduate, and I do say when you graduate, it will be a significant milestone. Mechanical engineers really make the world work. I'm sorry for the electricals in here, I don't want to do that. But we brought basic objects like the wheel, screws, inclined planes, cars, aeroplanes, paper clips, ships, bridges, skyscrapers, everything. And then there's all parts of engineering in them, I don't mean it that way. But it's been around for centuries. And unless there's some miracle of science that happens that allows humans to defy all the laws of mechanics, it's still going to be around for a while, and you guys are going to be part of the future of that. So the future of engineering, I said, is across many streams of mechanical engineering is across many streams that hold many promises to make the future a better place to live in. There's nanotechnologies, which is now out there, biomechanics, which is more, automobiles or flying automobiles in the future, robotics. None of those things, automobiles did, but none of those things really existed when I started here, right? The topics that I graduated were on courses like they're called the Jetsons or TV or sci-fi going forward. So something I tell all my engineers wherever I've been, and I hope it continues to resonate, and you guys take this and it resonates with you through your future. The first is technology change has never been this fast. Anybody disagree with that? Okay. And today, as it's the last day, it's going to be this slow, because it's only going to accelerate. The technological changes that happened in the last 50 years outpace that of the previous 5,000 years. And the technological changes that are going to happen in the next 5 years are going to outpace that of the previous 50, right? So some of this is unimaginable. Switching on a light switch to our medieval ancestors would have been unimaginable, right? My parents would have struggled to imagine a world connected with, or my grandparents would have struggled to a world connected with smartphones and the internet. My parents still struggle with that. And to be honest, it was unthinkable for me when I came to college. And I'll give you a reference. Our orientation when I came was we had to build our own computer. You didn't go buy it in a store, right? It didn't have a hard drive, it had a floppy disk. Anybody know what a floppy disk is? Yeah, been to museums, right? From that side, okay? It did have color on the screen. You could have green or orange with a black background, right? No pictures or screensavers of where you want to go on vacation or that, right? So today, it's still hard to imagine that arrival of technologies that's going to fundamentally change the world we're used to, right? And technology needs to continue to change the world for the better. And it's our responsibility and your responsibility to make sure that happens. So as an engineer, you're going to have the opportunity to make a difference, change the world in ways that, again, you can only imagine. Imagine being involved in the creation of artificial organs, pollution control that preserves the environment, perfecting the flying vehicle. Engineers make a difference in the world around them, saving lives, improving technology, preventing disease, and protecting the world. So I kind of want to leave you with three things. I don't have a slide from that side, but you all belong in the engineering profession. It was hard work to get here, and we need you. The world needs you. And when you're thinking about things, shoot for the moon. Okay? The next thing is, let's use your mentors. You'll benefit from their experience, their vision, and guidance as they go along. And the last thing I want to say is take risks, and don't be afraid to fail. One of the terms I use for my engineers is fail as an acronym. Does anybody know what fail as an acronym means? First attempt in learning. Okay? There are failures when you continue to do the same things 3-4 years in a row. Right? We don't want you to be Einsteins in the bad way. Don't do the same thing over and over again, expect different results. How do you go forward? So I just want to finish up with, you're the future of mechanical engineering. I'd like you to go out and turn that science fiction into reality, and your research, technical ideas, and inventions will expand the horizons of human possibilities, lifting everybody up in the world. So thank you very much, and I wish you all best of luck on this journey.
Once again, I do like to thank Greg Livelli for not only all that information, but also sharing his passion and how he started here at NJIT, and just overall teaching us that it's the first attempt in learning, and we should all hope to fail at least once. Additionally, I would like to ask Lawrence Simon to come up and speak. Thank you. All good. Take your time. Thank you. Hope I didn't butcher it.
No, that's problem.
Oh, good afternoon. It's a pleasure to be here. I'm Lawrence Simon, Vice Provost for Undergraduate Studies. I want to congratulate all of you for your work at this event. When you think about it, you work on a reverse engineering problem, which means that you gather information about the design of a product by isolating the different parts. The goal was to find out how the whole system works. Why do you think you have to do that? Why would you use reverse engineering in life? Where would you use it? I can think of 3 reasons. You need to troubleshoot something, or you need to go and fix it. The other reason, you may need to enhance the operation of the product. It's interesting because in addition to being the Vice Provost for Undergraduate Studies, I also do research in engineering, and reverse engineering has always been a passion of mine. The idea that you are looking at a process, you're looking at changes in the process, and people are asking you, what's going on? How do you fix it? The definition of a process, it's something that you understand the input variable. You know what to manipulate. Then you can explain the outcome of the process. You need to understand the inner workings, and the project that you worked on, the things that you do today, give you some insight about the inner workings, the different parts that are being used. And one thing that you discover as well is not only the isolated operation of each part, is how they all contribute to the overall system. As you know, in this endeavor, you needed to be observant and patient. So these skills, please remember to apply them through your time at NJIT. Remember the meticulous attention to detail and the time you spent figuring out the function and the structure of the different parts and how they relate to the overall system performance. By the way, one of the things that we do in my office is looking at courses that you will take at NJIT. How do they fit into the demand of your profession, of the field that you have chosen? So it's not, I look at it, it's not that much different from the classes, the courses in your major, and how they are connected to your success. These courses and projects are elements of your education designed to help you become accomplished and competitive. So you see, I dissect the whole process as well. I do exactly what you do. You are embarking on a world where critical thinking and process analysis are essential to the field. Another example of reverse engineering, when you're looking at patches, for drug delivery system, for instance. If you need to make any improvement to a patch, you have to understand how the patch that you have now, how it works, so that you can identify the parts that you need to enhance. If you don't do reverse engineering, you will end up looking at some irrelevant input variable. You will think that the distance of the patch to a desk, it's relevant to the delivery of the drug. So that's why those critical thinking, those analysis tools that you are developing here, that you are using, are essential for your formation in engineering. I want to give a special thanks to the Mechanical and Industrial Engineering Department, your professors, the judges, and the entire crew who organized the event and assisted you in this endeavor. Again, thank you. And remember, we expect great things from you. Thank you.
Thank you, Lauren, once again, and thank you for coming with such short notice and talking to us and giving us thoughtful advice. Now,
It's okay.
well, it's a video, but as you can see on the screen, Nick, do you happen to know what this is and what it is?
That is the Mobius strip. So essentially, if you take a sheet of paper and you take both ends, connect them, it creates one singular surface.
And this model was made as a mechanism animation in Creo parametric software, which all of the first year here in FED have been using Creo for their whole semester. And they built their models and reverse engineer using Creo. And the inscriptions on the 3 ball bearings are inspiration, innovation, and invention.
Those are the main guiding principles that we used when engineering our projects. Speaking of our projects, some of the first-year team speakers are here to give their lightning talks. First, can we welcome Michael Cardona and Kush Rana.
Is this a right presentation?
Yeah.
I thought it was the other one. There. How do I go next? Okay. Good afternoon, everyone. I promise I'll make it short. I know y'all want to go home. So Michael and I, we did the electrical pencil sharpener. We're team 1. And as you can see, oh, wait. You guys, oh, it shows there. Oh, there. It's confusing. So the innovation we came up with, we noticed that there's no way to actually hold the pencil sharpener. So we decided to add the handles on top, as you can see on the image above. And the bottom one, it shows like the insides, I guess. Next. Next up, we have the patents. You want to talk about them?
Good afternoon. So, regarding the patents, you can't really have anything without a patent, without an original drawing, without labeling all the parts and what you need to do. So, regarding the pencil sharpener, I've decided to take 3 original patents, one describing from each individual timeline, one from 1964. This one right here has almost similar almost similar parts to the electric pencil sharpeners that are used today. I'm not gonna talk about it. This one's from 2005 regarding the same original principles when it came to electric pencil sharpeners, same parts, except different design. Now, this is from 1934. This is when electric pencil sharpeners started to be more used within industries, schools, because of automation. What they decided to do here was, instead of having one cylindrical cutter, they decided to have 2. The problem with this is that you have rotating parts. With rotating parts, it doesn't really leave much room for anything, meaning there's a smaller debris tray. And to be honest, just like everyone else, I don't want to keep getting up to throw out the debris. So, yeah.
So the process, this would be the motor assembly. As you can see on the white cylinder, you can see that would be the motor. We have the green circuit and all the other small details. Next up, we have the cutter assembly. We have the cutter, chassis, anvil, the counterweight, and the retention clip to actually hold the cutter and the anvil in place. Next up, this is the card assembly. I have it, I have it right here. The process, here are more pictures. Passion. Okay, so I know this was a reverse engineering project, so how can we compare, everything we talked about so far, the patents and everything, it doesn't just come from scratch, right? There were innovations made beforehand, which kind of guide our future innovations, right? So the previous model, it had the chassis on the first 2 images. That's the chassis for the previous one, where you can see it had an internal gear. But with this one, they had a separate internal gear, which makes it easier for the cutter and the anvil to function. These are some drawings. Additionally, I'd like to mention the cutter itself. So previously, in the previous model, this whole thing was made of metal, but now only the cutter is made of metal. So this whole part is basically plastic. This reduces the weight of the whole pencil sharpener significantly, and it also makes it easier for the parts to function. And with this, the debris tray, as you can see, there's a small extrusion here. So if I can go back. So with the small debris tray, when you put it in, it sends a signal to the switch. So it clicks a switch, which sends us input to the circuit. And as output, the result is that the cylinder, it will start working once the switch is deactivated. So when you take this out, it's deactivated. If you try to put a pencil inside, it won't work. But if you put this back inside, the switch is activated, so it sends a signal to the circuit board or the motherboard, which sends an output to the motor to start working. These are some of the pictures we took. And yeah, before I end off, I'd like to thank Professor Money for being a great mentor and guiding us through the way. This was a good opportunity. I'm thankful, Professor Money. I'm thankful for Michael, the judges, and all of you. Thank you.
Thank you, Michael and Kush. And up next, I would like to welcome up Cassandra Schaffer, Sebastian Mercado, and Miles McGowan.
Hello, we are the Bee's Knees. We created the Bumble Brace. My name is Cassandra Schaefer.
I'm Miles McGowan.
And I'm Sebastian Mercado.
So, how does this work? What the world? I think I just turned it off. I don't know how this works. Oh, it's the wrong green button. So we designed an exoskeleton knee brace. We had the point of our design was to help out people who have rheumatoid arthritis. The entire thought process behind this design was based off of my older sister, who at around the age of 8 got rheumatoid arthritis in her knees due to Lyme disease. So we were hoping to help out people like her who have trouble walking. We decided to make the entire design focused around keeping it open sourced so that anyone can go and take the design and easily iterate upon it to their custom knee sizes, as no one has the same bodily anatomy. That's just not how that works. We also, the entire design was also based off the fact of how rheumatoid arthritis works, as the actual arthritis eats away at the cartilage between the knees, and thus the actual pain comes from the bone bending and essentially grinding into each other. So the design helps actually keep those bones separated, so during the bending process, there is no pain, or lessened pain. Our design overall was also trying to keep it as low cost as possible. So through our product costs about $45 to manufacture, which in compared to commercial braces, those can go up to $170, and we even saw some state-of-the-art stuff that was closer to $2,000. We try to have our design requirements include that it was comfortable and able to withstand the stress of day-to-day wear, not supposed to be like for extreme activities, but just walking around and overall being on your feet. It also is built to assist the user with daily activities, and as in climbing stairs and just walking. And it's also able to be lightweight and breathable and easy to put on, so that it's not like you're trying to put a whole machine on your leg.
So our first CAD assembly, as you can see here, we had a completely different, I'm just gonna show off the prosthetic on my leg now. We had a completely different hinge mechanism. It included 2 gears. We quickly decided that that was too bulky. Here you can see how originally the 2 pieces fit together. This was a problem for a lot of reasons, and when we printed it out, it quickly became apparent. Our first print, first off, had too little infill, and it fell apart in our hands. Secondly, we realized that with our measurements, it just wasn't lining up. We also realized that with such a long print time, this prosthetic was not really feasible for a normal person to produce. Over 2 printers, it still would take a whole day to produce. Our second one, as you can see here, was much more streamlined. We condensed it into 3 pieces instead of our original joints had 6 pieces each, so that would be a 14-piece assembly. So these 3 pieces were a lot easier to assemble. Our design improvements included that we only had 1 strut as opposed to the 2 on either side that we had earlier. We rotated the calf piece so this way it was easier to put on and take off. We added a honeycomb purely for aesthetic purposes, and we added an entirely new hinge mechanism.
All right, so to quickly give an overview of our manufacturing process, we began, everything was modeled in SolidWorks. We sliced everything in Cura, and we printed all of our pieces on the Ultimaker 3 printers in the makerspace. Additionally, in order to attach the gas struts that we ordered from Amazon for roughly like $15, we used brass inserts that were molded into the 3D print using a soldering iron, which allowed us to add our screws directly into the brass inserts instead of into the plastic, which would have added too much risk in terms of like the fragility of the plastic. If we can continue here. This is just a brief design comparison between the first and second model, and everything was much more streamlined. We added aesthetic details, and we simply cut down on the print time and the complexity of the original design. So in terms of future improvements that we would like to make, we'd like to add struts on both sides of our knee brace. We'd use weaker struts in order to make it easier for the user to bend their knee. We would also only use one like solid joint in order to allow for more flexibility within the twisting motion of the knee. And we would also use different materials and add padding to create a more stronger and comfortable fit for the user. So quickly, we'll just go over like some reflections of our project. The one thing that I learned really was just the value of rapid prototyping and the necessity of getting those first really rough prints out, because it allows you to see it physically what's wrong and what you need to fix in the future.
What I learned is that sometimes you have to be willing to let go of something that you thought was going to work really well when it just turns out it just won't, and learn from that iteration and just keep going forward.
What I learned, that making decisions that are critical in the beginning and also starting with smaller iteration pieces would be more wise versus having to iterate on a whole design, working on individual sections, and then just being able to rapid fire is very important. So thank you to you guys for watching. Obviously, this was a wonderful experience. Thank you to Professor Moon for helping us with some aspects of getting a hold of some pieces, as well as putting us in contact with a physical therapist to help give us our science behind how the entire arthritis works. Also, thank you to all the other students in our class who were willing to just listen and talk and help us work with our design. So, thank you.
Thank you guys so much for showing us your knee brace, and I love the name. Additionally, we would like to ask for Caleb Polilio, Jared Roberts, and Dominic Vogt to come present their findings.
How you doing? My name is Caleb Polilio. Today I'll be discussing the research I piloted through this experiment. I'm accompanied with Dominic Vogt and Gerard Roberts. We were prompted to re-innovate a clip fan, a portable fan that clips to most surfaces. And while my teammates focus on the other aspects of the project, I focus more on the blade itself. My slideshow. Anyone help? There it is. All right, so today I'll be going through my plan, the design, computational fluid dynamics, the flow analysis, physical testing, the results, and some acknowledgements. So my plan, I plan to design 12 different blades, with 3 different angles and 4 different numbers of blades. The pitches go by 5 degrees, 15 degrees, and 30 degrees, and 3 blades, 5 blades, 7 blades, and 9 blades. And then I'll design them and use CFD software to print out the blades and test them out, and physically retest to prove my calculations. So some notes to start. An odd number of blades works better for stability and provides less noise. And the wider the longer the blade, the more airflow it's able to generate, however, it creates more drag and resistance. And needs to be somewhere in the middle to fit all the blades that I'm looking for. And that's the equation for volumetric flow rate, V being the velocity that the air is coming off the fan, and the area where the fan is going. My hypothesis, I predict that 15-degree pitch with 5 to 7 blades will give the most airflow, and they will cover a good amount of surface area and cover less mass. And then the 5-degree pitch with 9 blades will be the worst, because it will have a small pitch and too heavy. So here's the design. Here's the original fan blade. Not much to it. These are my fan blades. You can see the 3, 5, 7, and 9, not taking into account the pitch of the actual blades. Now we're going to go into computational fluid dynamics. What it is, it's pretty much a computerized quantitative analysis that tests structures in terms of fluids. It's very useful and accurate, and it provides a cheaper way to analyze without actually having to prototype. Very cost efficient, but it's also very difficult to learn, and it's a big learning curve. And why it's important is because I was looking for a way to test all these 12 blades without actually having to print them all out, because that'd be pretty expensive. And I was looking around Creo, and I was able to find something called flow analysis with a fan with like some air protruding out of it. And I started playing around with it, and I could realize how difficult it was, but I was set to do it no matter how hard it was going to be. So yeah. The flow analysis and physical testing, that right there is the mesh that you have to make. So pretty much you make a mesh, it's kind of like a box around the fan itself, and you can have different boundary conditions. I was helped by Dr. Peter Below. He helped me through starting the process and being able to understand the program better. So I started with having a pressure going through and a pressure coming out with the fan going 1,000 RPM, but I wasn't seeming to get the right results. So it took a while, a long time actually, and I was about to give up, but I just decided to take a break, just sleep on it. And I woke up the next day, instant thought in my head to have the pressure going through a little bit higher than the pressure coming out by like 0.0001. And I ended up coming up with this. This is the base model. You can see where the airflow comes out, and it recorded 105.64 cubic feet per minute. Now this is the 3-blade. You can see there's a slight improvement, and you can see how the 30-degree spreads out the air more. And I was unable to do the rest of the 3 blades because there was a licensing error, and I couldn't get it fixed in time. So we'll just continue with this. This was my best one, the 5-degree, or the 15-degree with 5 blades. It provided the most CFM at 233, and you can also see the 30-degree spreading out the air even more. Same here with the 7-blade. Not as good as the 5-blade, but you can also see like the more amount of blades and the bigger pitch, even more the airflow comes out. And you can see it also with the 9-blade. It's pretty repetitive, but you can see how much the 9-blade 30-degree really pushes the air out, but it's not so effective. So this is my physical testing. I had to figure out a way to generate a physical mesh itself and test with the anemometer. The anemometer pretty much just test the velocity of the airflow. So what I did was I made this cardboard cutout 28 by 28 centimeters and 18 centimeters out. That's what the mesh was. And I was able to test it at 22 different spots and then average them together. And then I was only able to print one because the makerspace was packed for finals, and I was only able to get to one because I couldn't find a printer. You can see the pitch there at 15 degrees, and there's it set up. Here are the results. So I physically recorded 94.35 CFM for the original blade, and the CFD test came out as 105.64, which is a 10.7% accuracy, which I think is very good, knowing that I had to guess the RPM because it didn't give it to me. Now for the 15-degree blade, I physically recorded 101.45, which is still an increase, but it's not the increase that the CFD gave me, and there's some factors towards that. There's the print isn't completely smooth, so all like the ridges in the print caused friction, which slowed down the blade. It also wasn't balanced completely, so it wouldn't fully like go the speed that it was desired. And that proved a 121 increase in flow rate, which is pretty huge. So I proved my hypothesis there. Acknowledgements and what's next. I'd like to thank Dr. Peter Below for helping me through the CFD process and really being there if I had any questions. Professor Manny for motivating me and allowing me to like work on my passion. And Orlando Castillo and David Bailey for helping me in the prototyping phase with just tools in general. And yeah. So what's next? I'd like to continue my research on fan blades, maybe publish a paper, and take into account more variables because there's always more you can do with the shape, size, curvature of the blade. And I'd like to expand it into computer systems, cooling systems, pretty much anything, and a professor to aid me in that research. Thank you.
Thank you guys for presenting that, and thank you all the students who came up and presented and everyone who has been presenting. And as you guys saw, there have been judges going around and seeing you guys. So to the moment that most people have been waiting for, it's time to announce the winners and the stars of the showcase today.
Please welcome our beloved advisor, Feneza Hussein Ali, to announce the stars of the showcase. And we would like to thank Allison Tarifa and Chelsea Garcia for doing the points calculations.
We would also like to request Dr. Rao to congratulate the winners and to distribute the awards. Oh, no awards?
We have many winners will be notified. Certificates to follow winners will be notified via email. We have plenty of ties. Yes.
So
just say this. Just say this.
okay, wait, never mind. The winners will be notified via email when and where to pick up your certificates. Your group is called Please Stand to be Recognized.
Thank you.
Hi, everyone. Good evening. Thank you all for being here. I'm Feneza Hussein Ali, the undergraduate coordinator for the Mechanical and Industrial Engineering program. I'm here to give their certificate of appreciation first to the students who helped out today, and then Chelsea and Allison, who we missed a few minutes ago, two of the most hardworking women here tallying the scores, will announce the winner. We don't have any certificates to give because there were many ties, which is encouraging, so you will be notified, okay? So Tamur, first recognition and thank you. Isa. These certificates are given to students because they've slept here, it feels like, but they've been so helpful in all of this in getting the today's ceremony ready. So we're giving them a certificate of appreciation. Keaton, Shivam, Nicholas, our host, Victoria, our hostess, Matthews, we'll give this to him later, of course, Chelsea. Okay, and now for the awards for the lightning presentation and the clip fan, Dominic Vogt. Yes. Lightning presentation and pencil sharpener, Michael Cardona. Lightning presentation on pencil sharpener, Kush Rana. Lightning presentation on clip fan, Jared Roberts. And finally, lightning presentation on clip fan, Caleb Palio. And now Chelsea will be presenting the winners of the showcase.
Okay, so we will start with Moon's section. I'm sorry in advance if I mispronounce any names. First, for honorable mention, we have Barsina A. Abdi and Genesis A. Jara Lore. Please stand up to be recognized. Or not.
They had class.
Second honorable mention is Justin A. Francique, Mars J. Keklek, and Yarutine S. Merlo Perez, and Jack M. Tomasello. For second place for section N49, we have Pablo A. Baez, Hans S. Hugo, and Ayula S. Kalijaye. For second place for section N41 and HM1, we have as high. We have Miles McGowan, Sebastian A. Mercado, and Cassandra N. Schaefer. As well as Joseph W. Lepisto, Andrew M. Ramirez, and Robert Nerdase. For first place in section N41 and HM1, we have James P. Crowdell, Pablo Gillen, and Jacob R. Emmett. For first place in section N49, we have Tatiana Mejia, Rumesa Mertz, and Robin V. Earlrick. Now, for the star of the showcase in Moon section, we have Chadley C. Jeed, Michael Modatsos, and Timothy M. Nassim. Next, we have Professor Mani's sections. First, in section N43 for honorable mention, we have Michael L. Cardona and Kush A. Rana. For section N45 honorable mention, we have Sebastian Dominguez, Bethany Lopez, and Lucas E. Reinha. For section N47 honorable mention, we also have Alexander J. Huegler and Lucas F. Morais. There is also a tie within that section, so we also have Naga Sashshank, Dik Shitsula, Andre K. Mensa, and Tariq Unalan. For section N43, second place, we have Edgar Benitez, Michael J. McDyer, and Nicholas A. Mixich. For section N45, second place, we have Nicholas R. Kortenhaus, Alex C. Weimer, and Robert D. Wozjak. For second place, for section N47, we have a tie. We have Mateusz Babkowski, Lucia Hepkel Barkan, and Mark S. Shulkin. Tied with Abdullah Masood, Dominic Turek, and Camden J. Vogel. For first place, section N43, we have Paul J. Bayassi, Nicholas L. Long, and Francesco V. Viterbo. Section N45, first place, we have Eduardo P. Benavides, Christopher S. Falcone, and Christian A. Villar. Section N47, first place, we have Stoyan T. Boyajev, Wyatt C. Salazar, and Gian R. Tortola. Now, for the star of the showcase for Mani section, we have Caleb R. Polillo, Gerard E. Roberts, and Dominic M. Vogue. Congratulations to all the winners, and enjoy the rest of your night. Are we introducing anybody else?
Oh, the showcase is not over yet.
I'm just telling you guys to enjoy the rest of your night.
We just have to do a short presentation, so if you could just hang tight for a few minutes. Thank you. Yes, they all have it inside of their, yes, come on up. You have, yes. I know. We appreciate your patience. Thank you. Nicholas and Victoria will take over the rest of the ceremony.
Sure.
Sorry guys, but we're not done yet. So we would like to also give some appreciation, and if we can welcome up Rowena and Greg, just a little gift of appreciation of memory of NJIT. Oh, we have the, where's the pause? Okay. In memory, we have Elberhard Hall. A picture with the painter on board at the time. Thank you so much. Thank you. Thank you. And then, before we finish, for a final award, we need to give an award to a man who has been supporting ever since 2012 for the past 11 years, and we just have to recognize him as an alumni. And who might that be but the very same man that has been taking pictures of every single person here and of the entire event, and for the last few years who's been supporting Mani since the beginning. Can we please welcome up Zada Lead, and also please Dr. Roa to give a little gift of appreciation. He's not here. He left.
Aww.
Okay, we'll give it to Ms. Hossein then, and then you can give it to him.
We would also like to give one final welcome to Professor Moon, who was integral in getting this showcase made and in the state that it currently is and how good it is. We also want to welcome up Professor Mani, who has slept a total of 30 minutes within the past 2 days. Yep, you were speaking. Yep. All good.
Good evening. I know the meeting is stretching into a long duration, so I want to make it short. But it's very difficult. So I made a short list, which is about 2 pages long. So many people helped me to make this show a success, okay? So number one, I mean, I'm not going to elaborate too much. So number one, we are honored to have our dean here, and he's here for the entire event, and I'm sure he's happy, and we are really proud of that, right? So thank you, Dean. Yeah. So second, I wanted to thank is Mr. Mike Smullen. He was very useful to me, or helpful to me, in arranging the speakers, and he tirelessly worked in trying to get me contacts. And he has been helpful to me for a long time. This is not the first time. So I'm very thankful to him for all that. And CDC arranged the lunch for judges. So why am I thanking them? Because these two people, the speakers and the judges, are the most important people that we have to thank. And these two people helped me to bring them in here, right? So judges are here, right? And the speakers are here, the two speakers who came and spoke and gave us a lot of advice. They are actually alumni of our department, 89, 91, 92, right? Now, see, they don't have a need to come and spend their time here, almost half a day, right? They are willing to dedicate the time. The gift of time is the most important thing that one can give. I can give you you can give me like $100, I can give it to you back. $1 million, I can give it to you back sometime, if I have that money. But time, I cannot return that to you, right? So if they are willing to come here to spend half a day of their time and share their advice and enjoy all the exhibits here, we have to be really thankful to them. Yeah, thank you so much, and we enjoyed your visit here, and I hope you come back again, in future events and help us, right? And then the alumni connections, they help me to give small gifts of recognition. This is just a token gift. So within a small budget, we are able to manage that. So I'm very thankful to Alumni Connections and also the communications department. When I was wondering how to frame the, the certificates, they voluntarily offered me that red folder, right, where I can insert the certificate and give. I think they are using it for graduation ceremony. So I'm very thankful to them. So these are the people who devoted the time, right? The next person I want to thank is my chairman, right? I get, I mean, there is no limit. There's a seamless and extended support for me for whatever I can do for this showcase and make it a success, and is the great support for me, right? And second is my colleague Swapnil Moon, and is the most cooperative person I have seen in my workplace. So when I need something, he will send it right away. He doesn't talk much, but he is a man of action. He just, so I'm very thankful to him, and he's a very nice person, right? Then the next person is the Orlando and David. Orlando created that display. I just explained to him, but he created a wonderful display of all the brochures for over the years. And also he left some spaces for the current year brochure, which is not ready yet, and the one in the future. So, and he gave me ideas, and he made a wonderful display. Maybe useful for showing it to the ABET, the accreditation board that may come. They can tell them that we have been doing this for a long time. It's not new for us. Okay. Then in our department, there's Gina and Ivy and Lucy. She is not in our department, but they all help me a lot by suggesting, by giving advices, and dedicating the time and doing some work, right, when I want something that is done right away. And also my friend Fanisa, she is very helpful and cooperative in all the activities I am doing here. Okay. And the most important person I have to thank is who? No idea? It's you, because you brought the meat to the showcase. You did all the work. You came here and you were frustrated at times, right, with the amount of work I'm giving. But now you see the fruit of the work, right? So this should motivate you, and you should be willing to work hard and harder than what you did now. And that will propel you to further success, right? Fasad Ali, we recognize him, and the award we gave, is for his continued support, voluntary support, right, and wholehearted support, right. He always finds out the date of the next showcase, and he will reserve the time to come and help me by taking photographs, and he's a motivation for me also. It's good. And he was one of my students in these classes. And I have one of his, reverse engineering projects, which I showed to the open house people, because it's one of the easier ones that where you can learn quite a lot, right? Simple and very valuable one. See, I just want to mention that this would not happen without the help of all these various people I just mentioned, and I might have forgotten a few. It's not that I intentionally forgot, but a lot of people helped me over the last 3 months, or with the 14 weeks we have been working on this project, and also over the years, right? And next thing is, there are 8 students who are sitting in the front, right? I don't think, like 2 weeks ago, I was wondering how are we going to do this, because we need some students to do the work, right? So I generally train the students. I spend a lot of time in explaining to them exactly what is to be done, and I don't involve myself. I make them do the work. I am behind the scenes, right? So these 8 students, I did not ask them to come and help me. They came to my office, and the girl who was here as MC, she came to my classroom, and she was having some other class. She could not meet me, and she said, Professor, I want to help you with the showcase. Please tell me what I should be doing. So every one of those 8 students asked me, and that is the reason they are here. And they took the responsibility, and I think they did extremely well. I'm very thankful to them. And next, I want to say something, because I'm an old man, right? Older people talk and they just give advice. So I cannot break the tradition. See, I always tell some fables from India, some stories from India. my grandchildren love to hear all the stories. There was a story, I mean, I thought of this, I also think about this quite often, right? Because I see in my class, this may not be, it's not complaint. It is just a friendly advice for you. In my class, what I see, when you see a student, right, don't take it seriously, but take it in a positive way, okay? So they come with their hood, right? Under the hood, they have this buds, earbuds. I know that because their facial reactions, that's not a good idea, right? And I was mentioning this, to one of another older guy in our group when we were talking in my family, and he related a story to me, and I thought I should share that with you. So there was a monkey, right, in India. A lot of monkeys are there. So, and they placed like in a plate like a few bananas. In another plate they put like $200 or 200 rupees or whatever, some cash, right? What would the monkey take? The banana or the cash? Right? If the monkey took the cash, it could buy lot more bananas, right? But it took the bananas and ate and threw away the money and walked away, right? So wearing the earbuds in the class and not listening to the teacher, right? I go and stand and ask. It is not everyone. It's just a few students, right? It's a very friendly advice. It's not a good thing to use in a class because you don't hear after you put stuff something in your ears. So I'm not complaining, okay? I get bad remarks when you start advising the students. The next thing is coming back to the engineering side of the story, right? So the reverse engineering is a good idea. It's not for learning purposes. And you don't understand the value now, right? Because during the process of doing this, we discussed a number of things in the class. Why something is there, even a little washer, why it should be there, what does the gear do? When I showed the gear design in the class, this is not for a freshman class, right? And I also did a lecture there, how to use master model and create gears. I saw almost about 30, 40 students were making beautiful gears. And it's not it's at 4:30 level they teach that class, that they teach that how to, and also I explained to them some of the theory of gears, and when they go for a junior year in your machine design class, they would really love to hear that, and it will strengthen their knowledge. So it is because those students who did that, they were passionate, right? And also I saw a lot of teamwork happening. They were working together very well, and they all observed what I was explaining, and they were able to create the gears in the class. And so many gears, the hex bug, the spider, inside that there are about 20, 25 different gears. And how to determine the diametral pitch, some of the features of the gears without having a special gauge. And they were doing it so wonderfully well. And I was very pleased with the set of students. And this year's students were, I feel they are smart, they're getting smarter and smarter, right, with all the facilities that they're getting. And I wish you all success, right? And I hope you remember this class for a long time. And something that you'll remember later in your years, okay? Thank you.
Thank you, Professor Mani. And to finalize it, what we've been saying multiple times today, and if you're in Professor Mani's class, what you've heard the entire semester, and something that you should take away from today, I want everyone to accompany me on this. When I say, whatever you do, do it with
passion.
Yeah, do it with passion. Thank you very much. Thank you for joining us today for the 13th Annual Innovation 101 Showcase event.